Okay, so a very good evening to all of you. So today I'll be speaking on one of the very special topics in the context of grain boundaries, and that's about the special high-angle grain boundaries. So till date, what we have covered is that we have been initially talking about what is a grain boundary in a microstructure. Then how do we define a grain boundary? That is exactly the first part of the of my talk that I had covered. Then secondly, I had also spoken about the 5 independent macroscopic degrees of freedom in a grain boundary. Then this has been followed by the 3 independent microscopic degrees of freedom, although I've not dug deep into any of the degrees of freedom in the context of grain boundaries. And then thirdly, I've also spoken about, I've also spoken a bit, not gone that much deep, but yeah, of course, so only spoken a bit about, this kind of a curve where we have pardon me for some time. So it's so this kind of a curve which represents the variation of the grain boundary energy as a function of the grain boundary misorientation angle. And of course, the last session I had also asked you, why does this curve look like this, or why does this curve have this kind of a profile, where where we have in the low angle regime that which ranges from which means that we are talking of the grain boundaries which has misorientation angle ranging from 0 to 15 degrees according to the Reed-Shockley model. Why do we have a linear increase of the grain boundary energy with misorientation angle in the in the low angle regime, and this has been followed by a number of a number of tips of the grain boundary energy beyond that, even in the high angle regime. And so and the last session what I told you is that there are certain data points. If you look at this data point 122, 111, 311, all these are the grain boundary planes, and these grain boundary planes actually represent the planes for special high angle grain boundaries, or those high angle grain boundaries, which means misorientation angle of more than 15 degrees based on the Reed-Shockley model, which have low grain boundary energy. So of course, what so this is one of the very curious things to look at this in this particular plot, grain boundary versus misorientation plot, energy versus misorientation plot. Now the second interesting thing that we can see from this particular plot is that and I had also asked in the previous section. So today I'll also be answering that in brief. So that why when we look at this particular part or compare this particular part of this this grain boundary energy versus misorientation plot with this part of the misorientation plot, and we see that these two parts are nearly symmetrical with respect to each other. So this comes because of the 4-3-fold axis of rotation in a cubic material. So for example, the plot that I'm showing here belongs to aluminum, belongs to 111. I mean not 111. So I'm sorry. So it belongs to aluminum. So which is an FCC material, and there for all the different grain boundaries we have got this kind of a variation where we have in this particular lecture, this is the source from where this material has been taken. So there we see that the grain boundary energy has been plotted as a function of the misorientation angle in aluminum, where the special high angle grain boundaries have been very specially represented. So we can see very clearly that there are certain boundaries. That is, not all the boundaries in the high angle regime have to be random high angle boundaries that we have already covered in the previous session. In this session, we'll be speaking a bit about the special high angle boundaries, where we can say that there are certain boundaries that have special properties. For example, low energy. And what do we mean by low energy? This is a low grain boundary energy. Okay. So if we can look more, if we can look deeper, so what we can say is that if in most cases, but not all, of course, these boundaries are also special with respect to their crystallography. Okay. So let's so this crystallography is something which is going to which is ultimately for these boundaries. This is ultimately this term crystallography is responsible for yielding low energy to these boundaries. So so when we look into that, what we see is that when a finite fraction of lattice sites, okay, so this is actually this is one of the models. This is a CSL models, as we can see from here. So this is one of the models which has been devised in order to describe the special high angle boundaries. This is one of the most commonly used models. Of course, this model has model well definitely, since it's a model, it will definitely have a number of assumptions, and these assumptions can sometimes be extremely useful in order to simplify a lot of things, okay, which otherwise they cannot be understood using if you do not use these assumptions. But they, at the same time, these assumptions also also have a number of limitations, and we will be discussing about them in this session. So when we speak about the special high angle boundaries being described using this kind of a model, CSL, coincident site lattice model, we are basically speaking that when finite fraction of lattice sites between the two grains, because two grains are nothing but the two crystals which have difference in orientation. Of course, if it's a grain boundary, as I've already said, mentioned that both these crystals will have the same chemical composition, or both these crystals are similar rather. Only thing that they differ is in terms of the spatial orientation, isn't it? So across a boundary. So when a finite fraction of lattice sites, okay, between the two grains, or between the two lattices rather, coincide between the two lattices, then one can define as a coincident site lattice, or a CSL. Okay, so a boundary that contains a high density of lattice points in a CSL is expected to have a low energy because of the good atomic fit. For example, I will tell you and show from this very simple example that suppose if you look at this case, there is sigma 3 boundary. This is a very common example of a twin boundary, okay, in any cubic material, whether it's FCC material or BCC material, and this 60 degree 111, and when you say exactly 60 degree 111, as a last session I have said that this kind of a boundary, which is a sigma 3 60 degree 111, so this is 111 is the rotation axis, 60 degrees is the misorientation angle of this boundary. So this is a very special high angle boundary, which has got, if you look at the case of aluminum, it has got a very low grain boundary energy. Of course, now the other thing that I can tell you is that in the case of aluminum, there is a very rare chance that you will see a twin at room temperature, because of course aluminum is a high stacking fault energy material. But of course there are chances that you are able to see twinning even in aluminum. But of course, if you look at copper, if you look at the case of nickel, or even if you look in the case of SS304, AISI 304 steel, it's a fully austenitic stainless steel. So these materials have got low stacking fault energy, and of course the presence of a twin microstructure in these materials at room temperature is quite common. Unlike the case of aluminum. But of course, even in aluminum, there have been reports that we can still see a very small volume fraction of twins in a room temperature microstructure. So if you look at the case of sigma 3, now let's come back to the point. So if it is a sigma 3 60 degree 111 twin in the case of aluminum, so this has got a very low grain boundary, as you can see from, isn't it? It's a 111 plane. Now, and if you are looking at the other kind of a boundary, there is another kind of a sigma boundary, there is a sigma 11 boundary. So sigma 11 boundary and the sigma 3 boundary. Sigma 11 boundary is a 50 degree 110. Okay, I will tell you how these misorientation angles and the misorientation axis. Yeah, so sorry for it. So if we look very carefully in the case of this, so in the case of the sigma 3 and the sigma 11 boundary, okay, we were there. So so if we look at the sigma 3 and sigma 11, so we can see that the sigma 11 means that every 11th lattice plane in between the two adjoining grains will be continuous with each other. Okay, but whereas in the case of sigma 3, this means that every third lattice plane between the two adjoining grains, you consider this grain here, you consider the other grain here, and every third lattice plane, okay, between the two adjoining grains will be continuous, okay, in the case of sigma 3. So of course, the number of so in that case, the number of so the last as you can see that I mean the second last statement in this particular slide, the point in the slide, that is a boundary which contains a high density of lattice points in a CSL. Of course, a sigma 3 will have a higher density of lattice points in a CSL because every third lattice plane between the two adjoining grains is continuous with each other. But however, in the case of sigma 11, every 11th lattice plane between the two adjoining grains will be continuous. So if you consider a fixed volume, of course you have to consider a fixed volume, then there the number of coincident lattice planes, okay, in between the two adjoining grains will be definitely much higher for sigma 3 as compared to that as compared for sigma 11. In that case, for your sigma 3 boundary, your for the sigma 3 boundary, the energy, the grain boundary energy is comparatively going to be much lower because of the good atomic fitting, and this is of course because of a number of reasons. I'm not going into that much details. So so definitely this CSL boundary will have a much lower energy as compared to this boundary, the sigma 11 boundary, because of the higher density of the higher density of lattice planes in a CSL, because which are continuous with each other. Because every third lattice plane here in this case to the two adjoining grains will be continuous, but here every 11th lattice plane, I mean between the two adjoining grains, will be continuous. Okay, for the case of this boundary. So that we have to always keep in mind. Okay, so similarly here, this is also another kind of a sigma boundary that I don't exactly remember, but we can calculate this. Okay, so definitely here, this you look at sigma 1 to 2. Of course, this has got supposedly this has to have a higher sigma value as compared to sigma 11 as well. Because see, if all this is there is a local minima here, or there's a dip in the grain boundary versus misorientation plot here, but then the but then the minima is not that low. Okay, the minima is comparatively much higher. The value of the grain boundary energy at this minima is comparatively much higher than that for sigma 3 and sigma 11 boundary. So here, so this we have to keep in mind. The last point is that when we talk of the boundary plane, of course, the boundary plane matters a lot, because of course it's the grain boundary energy is largely governed by the crystallography, as we have said in one of the earlier points. So crystallography of what? Crystallography of the boundary plane, because grain boundaries itself or themselves are the dimensional or the planar defects. So in addition to the misorientation, of course, misorientation also has got a certain role to play, but it's basically the boundary plane or the the spatial orientation of the boundary plane. In other words, the atomic arrangement across the boundary plane or on the boundary plane, okay, that matters a lot in order to define the grain boundary energy, even for special high angle boundaries. So this means in effect that only pure tilt or twist boundaries are likely to have a high density. Of course, pure tilt and twist boundaries are likely to have a higher density of CSL lattice points. If we are looking at this point very clearly, I'll tell you. So this point means a lot, because when we look at the low angle boundary, so of course when I had told you in the initial in the initial session that when we talk of low angle boundaries which have the misorientation angle of ranging from 0 to 15 degrees based on the Reed-Shockley model, of course. So there, these low angle boundaries in a real microstructure, we see them in the form of subgrain boundaries that I also have shown you in one of the previous sessions. So there, if we consider the CSL model will consider these low angle boundaries, not all these local minima CSL boundaries, rather the low angle boundaries. So in the CSL model, these low angle boundaries will be considered as the sigma 1 boundary. And then if we now try to understand what is sigma 1 boundary, sigma 1 boundary means each and every lattice plane between the two adjoining grains will be in perfect coincidence with each other, or in other words, will be continuous with each other across the grain boundary plane, isn't it? But then, of course, so looking at them from the macroscopic point of view, we can say very clearly that that they may be continuous with each other. But then, definitely, as I will show in the next slide, that there is hardly any chance of a perfect coincidence of the lattice planes between the two planes, and that is what something which defines the 3 microscopic degrees of freedom that I have again mentioned in one of the previous sessions. So. So till this much, the take-home message from this particular slide is that there are two things. I mean, if you look at the low angle boundaries, where the grain boundary energy varies as a function of the grain boundary misorientation angle, we can see one very interesting thing is that when we move beyond 15 degrees, as I told you in the last session. So there we see that there are certain dips in the grain boundary energy versus grain boundary misorientation plot, and these dips basically represent the special high angle boundaries which have a low grain boundary energy as compared to the random angle boundary. For example, if you consider a data point here, a boundary with a certain misorientation, maybe this particular misorientation angle and this particular grain boundary energy. So this boundary is a random angle boundary. But then if you're looking at this particular grain boundary, so this has got a very low grain boundary energy, or rather to say the least grain boundary energy here, and it appears at this particular misorientation angle, and it is also in a high angle regime. If you're talking about the Ricci-Shockley model, then in that case, this boundary shall be called a sigma boundary or a CSL boundary. Okay, so similarly, this boundary will also be termed as a CSL boundary. This boundary also shall be termed as a CSL boundary. So here, and this is the first thing. The second thing to take from this particular slide is that if you are talking of this, if you are looking at this sigma 3 and sigma 11, because sigma is nothing but the inverse of the population of the coincident lattice points. Of course, we don't need to. I don't need to. I mean, for your level, I don't feel to cover that aspect to a large extent. Otherwise, it will lead to complex grain boundary plane crystallography. What I just mean to say is that if you're looking at sigma 3 and sigma 11, of course, sigma 11 is having, so we need to know the physical significance or understand this physical significance of sigma 3 and sigma 11 there. And if you're looking at sigma 3, this means that we are having only, I mean, each and every third lattice plane between the two adjoining grains will be in perfect coincidence with each other, is expected to have a perfect coincidence with each other. Okay, but if you are looking at this particular sigma 11, which means that every 11th lattice plane between the two adjoining grains will be in coincidence with each other, okay, or will coincide with each other. So this means the number of coincident lattice points, or the lattice sites rather, in the case of sigma 3 for a fixed volume is comparatively much greater in sigma 3, because every third lattice plane is coinciding between the two grains, as compared to sigma 11, where only every 11th lattice plane between the two grains is coinciding. So because of this, the sigma 3 will have a lower grain boundary energy as compared to the sigma 11. Okay, because the sigma 3 will definitely have a much better atomic fit as compared to the sigma 11 boundary. So these are the two very essential things that need to be taken away from this particular slide. Of course, this is one of the very interesting lectures by Anthony G. Rowlett. From where all these materials have been taken. So, I mean, you can have a look into this particular website, and this contains very excellent illustrations of grain boundary crystallography, because all the things about grain boundary and grain boundary plane, grain boundary crystallography, which actually govern the grain boundary energy. Okay, so those things are something which need to be understood very, very in a hugely animated fashion, in a hugely animated manner. I mean, it's one needs to visualize them. So now let's move on to the next part. So these things we have understood. I hope these things we have understood as well. So now, but now how do we account for the low boundary energy at the high angle regime? So of course, what we are saying is that we have a good atomic fit. Okay, but exactly what is happening? For which we are able to get only, only there are certain, if you look at the certain data points, there are very discrete data points where we have a very, very low, there is a sudden dip in the grain boundary energy. Okay, that appears at very, very specific misorientations, not it does not follow a hump, or it does not follow a range of misorientations, only that there is a discrete misorientation angle and a discrete grain boundary plane for which the grain boundary energy has got to attain a minima. Okay, even in the high angle regime. So now that thing, what we have to understand is that the CSL concept. So for that, for that we need to understand first that what the CSL concept is about. See, the CSL concept first talks about when we are talking of the two grains, okay, two grains, and we are trying to understand the special high angle boundaries by the CSL. We are only considering that there is a coincidence of the lattice points. We don't consider that there is a coincidence of, the CSL concept does not talk anything about the crystal, because lattice and crystal are not the same. Because if your lattice is having atoms or any motif, of course, then that will give rise to a crystal, okay, which have a translational symmetry, a long range symmetry as well. A long range order as well. So then we are talking of polycrystalline material. Of course, the CSL concept never talks of crystal. It only talks of lattices, adjoining lattices. Okay, or the coincidence of atomic planes in the adjoining lattices. with different spatial orientations. But then the main thing is that, as I told you, is that the lattices never actually overlap. I mean, there is obviously a certain even if you consider that there is an atomic plane which is continuous across a given boundary plane, of course that there will be a certain offset of one boundary plane with respect to the other boundary plane by a certain by one or two atom distances. Of course, and that has to be always taken care of by the three dependent microscopic degrees of freedom. Of course, that also has to be taken care of, and that basically arises because of the special high angle boundaries, which even today are modeled very commonly using the CSL concept. So it's around 70-year-old concept exactly. So here, what we can say is that if a fixed fraction of lattice sites in this concept is the CSL concept, if there is a fixed fraction of lattice sites which are coincident, then the expectation is that the boundary structure will be more regular than a general boundary. Of course, if you look at a general boundary or a random high angle boundary, where between the two, between the two lattices with a difference in misorientation. Okay, with a certain misorientation angle difference, or with the two different spatial orientations rather, if there is no atomic plane which is going to coincide with each other, so that basically leads to nothing but a random high angle boundary, isn't it? But then, if you are looking at the CSL boundaries, in that case, or in those cases, even if the misorientation angle between the two grains are more than they're greater than 15 degrees, 15 degrees, then also there are certain atomic planes which are continuous across the grain boundary plane, and that they appear at regular intervals, and that periodicity at which they appear basically determines the sigma value, isn't it? So that is something which the CSL concept talks about mathematically. So, so that is something which we also take, which this point also means that if there is a fixed fraction of lattice sites which are coincident, of course, in the case of CSLs, when the atomic planes are continuous across the grain boundary plane, then the expectation is that the boundary structure will be more regular. Of course, there should be some regularity because of the good atomic fit. Okay, and then a random high angle grain boundary or a general boundary, which where there is no coincidence of the lattice sites, or rather two of the lattice planes between the two, across the grain boundary plane, or the lattice sites across the grain boundary plane, and as a result, the energy, the resulting grain boundary energy is comparatively much higher. Okay. So now as we see that atomic positions, of course, now that I was focusing on the first on the first point, that lattices cannot actually overlap, and the CSL is only going to talk about the coincidence of coincidence of the lattice planes across or coincidence of the atomic planes between the two adjoining grains, okay, with two different spatial orientations. But now it does not talk anything about the atomic positions, and that's what this point means, that the atomic positions cannot exactly be accounted for in the CSL model. It is possible to compute, of course. Now, this is the thing, that it is, of course, it is possible to compute the density of coincident lattice sites in a plane of the boundary plane. But now this will go against the CSL concept, which has only to do with the lattice misorientation. Because see, the CSL concept only deals with with two things. The first is the misorientation between the two planes, because there are only very special grain boundary misorientation angles for which I told you that for which the grain boundary energy dips to a local minimum. Now, there is also another thing that has to be associated, and the other thing is that the reason behind why that happens is because the good atomic fit that the CSL model says is because of the more regular arrangement of the lattice sites. So this, in other words, that if in between the two planes, the lattice planes, okay, every third lattice plane, or no, the lattice planes repeat. There's a coincidence. The coincidence of the lattice sites, not the lattice planes, rather there's a coincidence of the lattice sites at regular intervals. Then that gives rise to the special high angle boundaries. But then, and this is obviously going to have a much higher, a much lower grain boundary energy than random high angle boundary, where there is no coincidence of the lattice sites in regard to adjoining grains. So there, in that case, and the other thing is that you can, it is also possible to compute. What this point which is that it is also possible to compute the density of the coincident sites across the plane of the boundary. There are a lot of computational But then the basic CSL concept has nothing to do with this, because the basic by the intervals at which the lattice points in between the two trains are in coincidence with each other. It does not have to do anything with the density of the coincident sites along the grain boundary plane. So that is something which has to be taken care of. Okay. So if we now look at let us try to see a simple animation. Now, if we are in order to make you understand this slides, I need to make you understand about the CSL boundaries in a very simple manner. If you're looking at these two. So these two grades, okay. So we are looking at these two grades, and so initially what we can say is that this is sigma 1 boundary, right? Each and every lattice plane is in perfect coincidence with each other. So here, here, each and every lattice plane is in perfect coincidence with each other. It's a sigma 1 boundary based on the CSL model. But now let us consider a boundary plane here. Okay, now let's consider a boundary plane here, and we can consider that this is a plane Y, because if you look at this is just a section, right, of a three-dimensional object. If we are just trying to look at a three-dimension, then we can see that definitely this is also the projection of a plane, right? And this is just a projection of a 2D plane, a two-dimensional plane. So definitely there is no problem of considering this particular line in 3D as a plane, and so we can consider them to be a boundary plane. Let us forget for the time being that they are the CSL boundary planes, rather they can be easily considered as the grain boundary plane. Now, the point is, now if we look at these two atoms, okay. Now let us look at these two atoms, and here, and the other very interesting thing is that if you are again, so this is one set of lattice points, okay. So this red is one set of lattice points. There is also other set of lattice points. We have to observe them very carefully. I mean, of course, it's hard to observe at this particular slide, because there is also other set of lattice points which are the green lattice points, and these red and the green lattice points coincide with each other. Of course, so this is again the perfect case of a sigma 1 boundary also. So these two, of course, when you are looking at red lattice points here and here, this in both these grades, these coincide with each other. But now, if you are looking at the coincidence between the red lattice points and the green lattice points, I mean the green lattice points I cannot show here clearly because they're in perfect coincidence with each other. That is also another example of a sigma 1 boundary. But now let us look at this again. Now let us look at this. Now suppose the aim, say initially, is to rotate, okay, is to take this plane, okay, take the rotate around, rotate across, okay, or rather to say that rotate across the x-axis, okay. Let us rotate this perfect arrangement across the not the x-axis, rather to say, if it's a crystallographic arrangement, then now let us try to rotate them, from coming outside the plane. I mean, if we are looking at this, this rotation is not exactly correct. So if we are thinking about, if we are looking at the computer screen, now let us try to rotate this the red lattice points with respect to the green lattice points. Keep these green lattice points fixed and rotate only the red lattice points. Normal to. So normal to the plane of the stream. Okay, so normal to the plane of the stream. So what do we see now is that if you look at the second, if you go to the second slide, you can see very clearly that so the red lattice points are actually shifted with respect to the green lattice points. Okay, so although these two lattice points are nearly in the same position, at this spot, the red and green lattice points are nearly coinciding. But red and green lattice points, they are shifted. If you are looking at the earlier slide where we are talking of this and this position here, so in the next slide we can see that there is a shift of the green lattice site with respect to the red lattice site in both these positions. Okay, so similarly, if we are now looking at we are rotating further, there is a further shift. Okay, so you see the entire idea is to bring the so the entire idea is to bring this and this, these two lattice points in perfect coincidence with each other, and for that we need to do some rotations. Okay, so for that, as we can see very clearly, so if we are rotating more, okay, and we keep on rotating after a certain so now as we see that after a certain number of rotations, here it is around 10, a certain number of rotations and by a certain angle which is equal to 37.1 degree about the 001 plane. So so the lattice plane which was here has completely been brought into coincidence with this lattice point here, and similarly the lattice point here remains unchanged. So what we can say, okay, so what we can say is that, so what is this x and y? So first of all, now let me explain what is this x and y. So x and y is nothing but uh, so if you look at, I'll be explaining that, but now let us first understand why. Why this certain amount of angle. I mean, how to compute this angle, and how to know that whether this is the plane across which the rotation has to be performed or not. So the angle of rotation can be determined from the lattice geometry, which means that explain more, the discrete nature of the lattice means that the angle and the sigma values are always determined as follows. That is, the if you look at the theta, this is the misorientation angle across the CSL boundary. So there, the tan of theta by 2, okay, tan theta by 2 is equal to x by y into square root of s square plus k square plus l square. And where I was talking of the sigma, sigma is nothing but y square plus x square into h square plus k square plus l square. Okay, so where x and y are nothing but the coordinates of the superimposed point. Okay, so the superimposed point. So this is the superimposed point, isn't it? So so we have to know. So this is the x and the y coordinate. We have to always know. And in general, what happens in the case of CSL boundary is that the x is obviously much lesser than y. Okay, so y is the vertical. So it's the vertical. Distance, and x is the horizontal distance, isn't it? So the x is always lesser than y. I mean, in general, this is the case for the sigma boundary, and this actually we can obtain. I mean, this x and y, if we want to really have such a group, we have to do some rotations and then try to see how we can obtain the different sigma boundaries. So this is just a very simple example of this of the sigma 5 boundary. Well, the equation becomes very simple because the tan theta by 2 is equal to x by y into square root of h square plus k square plus l square. HKL is nothing but the green boundary plane. So if we just look at this 001 plane, so 001, so it doesn't make much of a difference, right? So 1 square, the square root of 1 square is 1 only, so that is very simple. So tan theta by 2 is equal to x by y. So the theta we can easily calculate. It is equal to, theta is equal to what? 2 into tan inverse of x by y. Okay, I mean the square root of x squared. This term is equal to 1 in this case because it's a 001 plane. Of course, we can. It's also possible. If one knows this HKL value, then it is possible to compute the theta. And then secondly, if one also knows about this, or if one knows about the sigma value, and sigma value, then it is also possible to compute this HKL values if provided that the theta value is known. Okay, so based on this, we can actually understand, we can actually find out the values of the different sigma boundaries. Now, the other take-home message that I want to provide is that this, the sigma value is always odd. I mean, it can never be even, because suppose, for example, I'm considering, I've been talking, if you observe very carefully, I've been only talking of sigma 1 boundary, sigma 3 boundary, sigma 5 boundary, sigma 7, sigma 9. I mean, of course, the people have even gone up to around sigma 13 and all, but of course, in real life, I mean, in real terms, a sigma 13 boundary doesn't make much of a difference. I mean, it is definitely not expected to make that much of a difference in a microstructure, is what is my personal opinion, because sigma 13 boundary means that there are only after every 13, or rather to say, each and every 13 lattice point between the two adjacent grains, okay, is in perfect coincidence with each other. So it is not expected to to affect the properties of a material to the extent as that which can be expected from the sigma 3 boundary. Of course, where every third lattice points in between the two adjacent grains are in between the two adjacent lattices rather are in coincidence with each other. So for that, for that, in the case of cubic materials, the two very common sigma boundaries, or rather to say these are the twin boundaries in the cubic materials that are to be considered are the sigma 3 and the sigma 9 boundary. Now the sigma 9 boundary is the second order twin boundary. Because because of course it's because of a simple mathematical relationship, that is 3 square is equal to 9. So it's a second order twin. Sigma 9 is considered to be a second order twin boundary in a cubic material. Of course, sigma 5 boundary is also quite important, because I will be conducting a next session on why these, why to understand the sigma boundaries and why is that important. Okay, why the presence of sigma boundaries, or how to that is when we engineer a microstructure. Why the presence of sigma boundaries instead of random high angle boundaries is very important. not for engineering certain properties or to enhance a number of properties. Okay, so I will not discuss that today. So I will conclude my session with this discussion today. That for this, so with just the take-home message from this particular slide, it is that when we talk of the two lattice points and we talk of the coincident lattice, the coincident site lattice concept or the CSL concept, what we need to talk about is that when we have, if we consider the theta as the as a misorientation angle between the two lattices, and we have the HKL, which is nothing but the grain boundary plane. Okay, so there, so how to find out? So in absence of either of the values of HKL or theta, the grain boundary plane or the misorientation angle, if we know the value of sigma, then we can definitely find out the value of HKL provided the theta value is known. Okay, and then similarly, if we know the value of HKL, of course, it is simple and straightforward. That is, only the thing that we have to know is the x and y, which are nothing but the coordinates of the superimposed point. And then from there, it is directly possible to obtain the theta value, okay, or the misorientation angle value for a particular say sigma boundary. So the boundary that I've been talking, if you put all these this thing here, okay, if you put all this these values, there is a theta value here in this equation, 37.1 by 2, and x upon y into square root of this, which is ultimately going to lead you to 1. So ultimately you'll be able to find out this the sigma value is equal to 5 in this case. Okay, so which means in a cubic material, rotation of one lattice with respect to the other by an angle of equal to 37.1 degrees about 001 plane will lead to a sigma will lead to the generation of a sigma 5 boundary. So with this, I hope you understood this class. But of course, this session, I'll definitely be sending a recording of this, circulating the recording of this to all of you. So thanks for your patience. Any doubts, please let me know by mail or in the Google Classroom forum. Thank you.